2/4.
Okay, so in 6.2, number 19, what it's a sentence, and it says the rate of change of n is proportional to n. You know, they should have said directly proportional, but I guess that's what they mean. The rate of change of n. So I guess I should write the rate of change of n. They didn't even say with respect to t or whatever, but maybe I'll use t or x. But the rate of change of n is proportional to n. Okay, so is directly proportional to n. Now the truth is, that's the same DE I wrote down the other day with y's. I wrote y's because I said the rate at which an amount of stuff changes is directly proportional to the amount of stuff you got. I mean, I wrote down this famous DE just the other day.
Right.
The rate of change of an amount of stuff over time is directly proportional to the amount of stuff. And then what we did was we learned how to solve this, and I like you to know those steps, but at the end of those steps, here's the solution to this DE. And it's the classic exponential growth or exponential decay model that we use for a lot of good word problems. So I could just write down the answer because I know it. Do you see what I'm saying? Right. But we can do the steps. Do you want to do the steps?
Yeah.
All right, we'll do the steps one more time. We separate and integrate. To separate, you multiply the dt over here, and I think you divide by this n. So dn over n equals k dt.
Yep.
A couple algebra moves there to separate. Now I'll integrate. I'm integrating this with respect to n. You know, just the fact that it's an n makes it look weirder to me, but it's still the same old math. It's the natural log of n, right? And I integrate this, with respect to t. So I think I get kt plus c. So we e both sides now, because we're trying to solve for n, so we e both sides. So the e and the log cancel, we get n equals, and then the fancy little move I do here is that I have e raised to all that, and I can call that e to the kt times e to the c. Because multiplying bases means I should add exponents. So this is kind of an important step I'd like you to understand. And anyway, now, the e to the c, I think I'll just call an arbitrary c. So you're right. There's my answer again, like we predicted. Here's the answer. In general solution to this differential equation. This differential equation started in words, by the way, and then we wrote this math, and then we solved it. Cool. But now there's some data they give me. They tell me when t is 0, n is 250. When t is 1, n is 400. What is the value of n when t is 4? See, those are good questions. Those are classic kind of questions for a word problem where you have some data. They said when t is 0, n is 250. They said when t is 1, n is 400. And then they said when t is 4, please find n. Bless you.
Thank you.
That's what they said.
Right.
So they're giving me this information, and it's two pieces of information, and I think two pieces of information are going to be helpful to find the two unknown constants, c and k. So it's that preliminary work. You use those, you plug those in, and that helps you find c and k. Then you have the model, you have the specific model, and you answer the question. So that's the game. It's kind of algebra from here on out. But it's good algebra. This e and log algebra is kind of good algebra. Anyway. If you plug in a 0 for t and a 250 for n, you quickly find out that c is 250, don't you? If you plug in a 0 for t, you get e to the 0, you get c equals 250. You guys with me? That first piece of information, that first piece of data yielded that. The next piece of data will help me find k. Let's see, how do I do that? I plug in a 400 for my equation here. I plug in 400. Now I know c is 250, and I have e, I don't know k, but t is a 1. Plug in, it's like plugging in an x and a y value. There's t in there. Cool, I do a little algebra to find k. It's not too difficult. I would divide by 250. Divide by 250. I've seen some students subtract right here. That's pretty bad. That'll kind of ruin the answer.
Yeah.
So you divide by 250.
Okay.
Because it's multiplied. So you divide by 250. You know, I can cancel a 0. I can call it 40 over 25. I guess I could make it a decimal. What is it? Is it
1.6.
That's 8 over 5.
It's 8 over 5.
1.6.
It's 1.6. You're not rounding that 1.6.
No.
Then I'm happy. I'll just keep, I'll call it 1.6 equals e to the k. How do you get k? You ln both sides. So the ln of 1.6 is k. And the truth is, you could share that decimal with me, or just leave it like that. I mean, that's k. I mean, it's not necessary to tell me what that is. What it is, it's some 8 or 10 digit long decimal that I've advised you not to round off, is what I've advised you. So I might just keep it like that. So now I got my c and my k. So if I have my c and my k, what I have is, instead of this generic model, I have a specific model here. N, or specific equation, equals 250 e to the ln of 1.6 times t. And their question was, please plug in a 4 and find n. So it shouldn't be too hard. There shouldn't be really a debate about this. If you plug in your 4, you multiply that, you e that after you multiply it. I mean, at some point, I do pick up a calculator now, I guess. I plug in a 4, I multiply that, I e that. After I e that, I multiply by 250, and the final answer is 5,000.
1,638.4.
1,638.4.
Exactly. And we'll round it.
Yeah.
No, that's what I got.
Okay.
Exact?
Well, it's probably rounded. No, it's
Okay.
right. It's rounded.
Well, the
But
answer in the back.
I don't care if the answer is rounded. I want the. Okay, go ahead. The answer in the
No,
back.
the answer in the back was 8192 over 4. It was a fraction. And
That's
that's
like
pretty
five.
far off. I mean,
You know, that's
Actually,
that's divide by 5.
Wait a minute,
I
it's
just-
over 5.
Divide by 5, so I
I
think
just
this
ran
book
to a
here.
fraction. I get 81 and
Yeah.
Oh, is it?
Same thing.
8192 divided by 5. In the back it was 4. Okay, they made a mistake.
All right.
I think somebody was drinking when they were making the textbook.
That's right.
Working on this one. He's trying to figure out what I'm doing wrong.
Yeah, that's the second little error we ran
Yeah,
into.
yeah.
Oh,
That's
there's
funny.
quite a few.
The second one in the first week.
Yeah. Okay.
Okay, that
So you looked up the answer in the back of the book. You thought it was wrong, but actually the back of the book is wrong.
right.
Right. The answer is this
They
answer is
had put
correct.
5, it would have been the exact same.
They had this as an answer, and that's wrong. Huh?
Yeah.
All right. That's weird of them. Yeah.
Unless they're probably thinking of the time being 4. And
Right,
they just
right. Right.
You know what I'm saying? T is 4.
Right. Right.
I don't know.
I don't know either.
Just saying.
Okay.
I feel better.
Okay, good. I'm glad you feel better. That's what this class is about. Make you feel better.
I still
No.
have it.
Any other requests? Or concerns or worries or requests?
21.
21. 21. See, 21 is kind of the same game. Here's what they say in 21. They say that this is the model for all these problems here. Well, for 21 through 26 here, 24, and then they give me a picture of. See again, this is sort of a whole family of things. And then they give me a picture of this kind of one member of the family. And they give me some specific points that he goes through. In 21, it's 0, 1/2, and 5, 5. 5, 5 is a point, and 0, 1/2 is a point. See, this is good old exponential growth, maybe, if k is positive. Of course, when I look at the picture, it looks like exponential growth. And they just want me to go through these 2 points. You know, that's a lot like what we just did.
Yeah.
We had a model, and we had 2 points, didn't we?
Yeah.
And we used the 2 points to find c and k. In this one, then, they had an extra question. But this one doesn't have an extra question. Basically, use the 2 points, find c and k, and you're done. What we're learning, maybe, after doing a few of these, is that that initial value is c. C is the initial value. Now, what does that mean? C is the y value that corresponds to t equals 0.
So C would equal 1/2.
So C would be 1/2. You could just memorize that, but the truth is, plugging it in yields that very quickly. Plugging it in says y is 1/2, and t is a 0, so you get e to the 0, so very quickly c is 1/2. Right. So now my job, so now I know c. So now my job is, so that point gave me that information. So now this point will probably help me find k. This point says y is 5. By the way, now c is 1/2. E to the k, and t is 5. And I just solve for k. On your mark, get set, go. I'll race you. Multiply by 2, that's a 10. E to the 5k. Take the ln of both sides. The ln of 10 equals 5k. Divide by 5. K is the ln of 10 divided by 5. And I can stop there, or I can make it a decimal, or just call it that. But we've,
there's no fraction.
well, and by the way, what it's not is it's not the log of 2. Please don't divide that. That's illegal math. Right. It's the ln of 10, that quantity divided by 5. The 10 is not divided by 5. But anyway, that's it. I don't really care. You guys were given, you picked up your calculator, you gave me a decimal. Guess what? I don't care. I mean, I don't mean to dismiss you, but so here's my answer. You know, I could write 1/2 is c 1/2. E to the, there's my k times t. I mean, right, I got this little nasty k times t. That's okay with me.
Okay.
You want to take the e and natural log and just get rid of both of them?
You know, be careful about that, but you're kind of onto something. All right, so hold on. So now I do want your decimal. What decimal did you tell me this was?
0.4605.
And on and on and on and on. This is the one I sort of told you not to round. But anyway, so if I did decimalize it, you're saying it's 1/2 e to the 0.4, what did you say? 0.05. Yeah, that's good enough. Okay, t. Are you guys okay with that? I mean, that's k decimalized. Here's k undecimalized. All right, now I want to chase down his thought that he just mentioned. I'm going to move over here. So I have this 1/2 e to the ln 10 over 5 times t. Okay. So he was mentioning, can we like simplify this a little further by canceling that e and log? And you know what? Maybe you can, but you got to be careful about how you do it. In a way, we have an issue here right now. There's something in the way. You know, when I have an e to a log, the e and the log cancel. But if there's something in the way, you can't cancel it. I feel like...
I mean, maybe if we pulled out the 1/2, got another ln for the other side so that we cancel out that first d.
Well, no. Okay, hang on. No, please no. I mean, no. Basically, no. I don't want to do that, right? What I want to do is, I want to clean up this e and ln. I don't want to introduce another ln. I want to clean up this e and ln, and I think I can, but I got to rewrite this. Look, see, I wrote that t multiplied on the back end. I'd rather multiply the t on the front end. And who else is multiplied out front of this?
1/5.
Kind of a 5 or a 1/5, so to speak. So I have a t over 5 in front of this ln 10. That's kind of why I can't cancel the e and the ln. Now, what can you do with a t over 5?
You can put it as an exponent on 10.
Oh my God, you can put it up here as an exponent on the 10. This is log properties. But that gets it out of the way, and now you can cancel the e and the log. And so now I do have this, 1/2, oh my God, what do I have? Base 10 raised to the t over 5. Wow.
Base.
Well, I move this up,
Yeah.
then I'm allowed to cancel the e and the log, and I'm left with this base 10
Yeah, that's
raised
what I
to the...
got. Okay.
But the truth is, that's the same exponential function as that.
Either 3 of those work, right?
What'd you say?
3 of those, like the first one we did when we did simplify the dial in, it would still work. Before you did all the log properties, that one would still work, right?
Excuse me.
The top one.
Yeah, he was just chasing an extra
Okay.
answer.
I'm not sure what your question is. I'm losing
Just
track
asking
here.
if with the answers that we have, are they all okay?
Well, right.
So
Where was the answer? Here. Okay, because the question was, please find the equation that hits these
Right.
points. You know, please find the equation that goes through these points. So we find C and K. So we did. We found C and K. That was a long time ago. That was an hour ago. No. But we found C and K, and there's my answer with a. And then I decimalized the K, so there's my answer. These are all good answers. But he mentioned how you can cancel the E and the log, and I said, well, you know what? You're right, but you can't just cancel the E and the log. You got to do it very carefully.
Right.
And you got to get that 5 out of your way, or that 1/5 out of your way, and you really got to get that T out of your way also. So I just showed you how to do that, which is not necessary at all. Nobody really wants to do that, but it's interesting in a way.
I was thinking that.
And what I'm saying, it looks totally different, but it is equivalent to those guys. It is equivalent to those guys. The algebra proved that, I guess. I want to do one of these radioactive decay problems, so I'm going to grab one here. Maybe I'll just do number 36. So in the book, we're in 6.2. Bless you. I'm going to try this number 36. Number 36 says I'm dealing with plutonium 239, which is a radioactive element. Does it tell me the half-life of plutonium 239? 24,100 years. Now let's just pause there a second. When they tell me the half-life, again, I mentioned this the other day, I think.
Yeah.
But maybe I didn't make it real clear, but when they tell you the half-life, basically you got K. But you have to, I'm not saying that's K. I'm saying by telling you the half-life, it can lead you to find K quickly. So I think maybe I should do that first. Let's find K. And the book gives you a little formula. Here's the formula to get K from the half-life. I'd rather you I like you to memorize certain formulas, but I also like you to think your way through things. I mean, here's how I thought about this. I know I'm using this model, and I know that if I start with some unknown C, that if I plug in 24,100 years, how much stuff will I have? If I start with C, in 24,000 years, I will have half of C. So I'm going to do that. And I'll have half of C if I wait 24,100 years. And even though, I said this the other day, I'm repeating myself a lot, even though you have 2 variables here and you think I can't solve for these 2 variables, very quickly one of them disappears. If you divide by C and divide by C, it's gone and you can find K. So knowing the half-life and knowing this concept leads you to K. Here we go. If I divide by C, it's gone. And then I would take the ln of both sides. If I take the ln of this, I'm left with K times 24,100. I would divide. So here's K. Was that too fast? Your book kind of says, hey man, here's a formula for K. K is always the natural log of a half divided by the half-life. That's what they say. They're right. But I just stumbled into it with this knowledge here.
That's
Yeah,
a lot
could you call
easier.
C 1 at least for an existing quantity?
You know, I mean, there's nothing in the problem that says C is 1, but just to help you think your way through this problem, maybe you're saying, let's just pretend C is 1, then I'll know this is a half, and you know what? You'll end up in the same place I was. I'm just a little worried about that because nothing in the problem said C was 1. My point is you don't know C, so you want to call it C equals 1. I'm saying you can do it with an unknown C. You can. Again, that's a decimal of some type. Can you tell me what that is? Negative point.
Negative 2.876129938 times 10 to the negative 5.
Thank you very
You have to
much.
move it.
All right, so
So
that
So
means you're
that's
gonna,
like negative 0.0000.
wow, so it's right because it was 10 to the negative 5, so you're saying maybe it's that.
Yeah, 2.876129938.
All right.
And that's all the decimals my calculator can handle.
Well, good, thank you. You know what? I might just stop right there.
That's where mine stops.
All right, I'm gonna stop there. Should
So
be good
really
enough.
small.
All right, cool. We found K. Now, what was the question? The question was, there was a little chart there in the book, and what they're looking for is the amount of, okay, what they want is the initial quantity. Now, the initial quantity in this problem was not given, so that was unknown. Then they want the amount after t equals 1,000 years, right?
Okay.
Is that what they want? And they didn't give me that either. They left that up blank. But then they did give me this one. That after 10,000 years, is that what they did? After 10,000 years, they did tell me how much was left. What did they say?
0.4 grams.
0.4 grams. Okay, thank you. Thank you. So it's my job to let's see. Oh, okay. You know, usually these problems, we've been working today, and to work with this formula, we've needed 2 pieces of data to find C and K. You know, I look up here and it's, oh crap, they only gave me 1 piece of data. Well, wait a minute. We already found K, right? Right. Knowing the half-life was another piece of data, and I already used it to find K. Right. So really, I'm in pretty good shape. All I need to do is I take that 1 piece of data and help me find C. All right, listen, I'm not sure how clear I made this the other day, but it is, when you're doing these problems, they're very algebraic, as you can tell, but when you're doing these problems, it's very advantageous to rescale time to your advantage. And I like the given piece of data to correspond to t equals 0, because then I got C. So I like to rescale time to my advantage. So I'm allowed to do that, and I will do that. I'm going to call this t equals 0. I had 0.4 grams. Now, if that's t equals 0, which I know it kind of counteracts what you're thinking, you want to call this t equals 0, right? But I want to call that t equals 0 and just rescale this thing. It'll work. Let me think now. If I'm calling that t equals 0, then what do I call this? It looks like it's 9,000 years before 0. What's 9,000 years before 0?
Negative 9,000?
Yes, ma'am. This is the initial quantity, which must have been 10,000 years before 0. What should I call this?
Negative 10,000?
Yeah. So I'm rescaling time for my advantage. So now, again, I'm trying to find this model. I know K. All I want is C. C is the initial value, but wait a minute. It's not this initial value. If I rescale time, It's this initial value. C is always the value that goes with t equals 0, and we made that be this. It just makes it easier. Instead of struggling to find C, I got C. So now I got this model. Y equals 0.4. These markers are bad markers. 0.4 e to the k negative 0.000028761 t. That's my model using this cool fact. This cool fact led me to that C is a 0.4. Now, I have to answer the questions. How do I answer these questions?
Plug in the t's.
Plug in negative 9,000, thank you. Plug in negative 10,000, thank you. Yeah. Can you help me with that? Again, it's just a matter of using your calculator carefully. It'd be a shame to screw this up at the end, right? I mean,
for 1,000 years, I got 0.518176641.
okay, now, okay, so I always warn you about, let's not round off this k too much. But when we get our final answer, I don't mind rounding it, because it's the number of grams. Anyway, what did you say? Let's make it 2 or 3 decimals. 0.5?
0.518.
Okay, 0.518 grams. Cool, thank you. You guys don't agree?
No, I was double checking him. He got it right.
All right, so what am I doing? I'm plugging in a negative 9,000. Is that what you did? Don't forget, we rescaled time. We rescaled time. So we're plugging in a negative 9,000 times that. After you multiply it, then you E it. After you E it, then you do that. I don't know. Or you type it all in one big equation.
I got 5.32.
I got 5.33 for negative 10,000 there, but for negative 9,000 I got 0.518.
Oh, okay. So people are agreeing with this.
Yes.
Yeah.
0.533.
And this is
0.533.
5.33?
0.533.
Oh, 0.533.
Yeah, it's not that big.
It's not that much. I don't know. If 3 or 4 people are getting it on their calculator, I tend to go with the 3 or 4 people. I can check it with my calculator. Okay. Cool. But that was smart of me. That little rescaling of time, that was kind of smart of me. It made it kind of easy, I think. You know, we sort of did that yesterday with the settlers in Massachusetts, right? I mean, I don't know. They landed in 1620. We called that t equals 0, and then we rescaled time. I didn't quite say those words, I don't think, the other day, but that was what you kind of want to do.
Wish I could do that in my homework.
Well, this is your homework.
No, rescale time.
All right, so you guys plugged in these numbers and got these answers, and I think you're right. Sometimes after these radioactive decay problems, you could try a couple more in here. There's a little batch of them there where they give you one and ask you for the other 2. Sometimes after you do those, you can sort of check the reasonableness of your answer. Watch. You know, if we did start with 0.533 grams, that's how much we started with, then how much do you have after 24,100 years?
Half.
Half of that, right? That's the half-life. So then you have roughly 0.2526, maybe something.
265.
266.
So you would have 0.75 of the original actual 1,000 years, roughly.
Well, okay, good. So right. So from here to here, we lost half of it. So in 10,000 years, we might be roughly halfway between there.
Actually, I think a little less.
Yeah, less than halfway. What was it in 10,000 years? What was it? It was 0.4 grams, right?
Yeah.
Yeah. Anyway, it's reasonable enough for me. Yeah. I was just sort of checking the reasonableness, vague reasonableness of the answer. I'm kind of happy. There's another good one. I like 38 is sort of a word problem that's good there. Let's talk about that one real quick, and then we'll move to something else here. 38 is a little word problem. It talks about carbon-14, I think, again, this is our model. And 38 is kind of this word problem. Carbon-14 dating assumes that the carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, the amount of carbon-14 absorbed by a tree that grew a long time ago should be the same as the carbon-14 absorbed by a tree growing today. Okay, that's the assumption. A piece of ancient charcoal that contains only 15% as much of the radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal? Wow.
Wow.
All right, hold on. And then they say the half-life of carbon-14 is 5,715 years. So we're talking about carbon-14, the half-life is 5,715 years. So I can plug that in and get K. I'll just do that quick. What do I do? Oh, I'm plugging in a half over here and a 1 right here. I kind of see his point, right? You guys, is that okay with you? Well, what did I say? I said you don't know C, then you plug in half a C. But then you divide by C and you're right here. And then you take the log of both sides, and the log of a half divided by the 5,715 is K. You guys okay with that? I skipped a couple steps. I took the log of both sides, then I divided, and I got K. Cool. Yeah, anybody want to give me that decimal? What is that decimal? Negative.
Negative 0.0001212855596.
Wow.
I would round that to 8.
That's negative 0.000121285
596.
596. Wow.
Oh, to the negative 1. Oh.
You could round it a little less than that, perhaps, but not too much less. I warned you about that. But anyway, okay, all right. Now, what's the question? I dug up this ancient piece of charcoal and I tested it, and it only had 15% of the radioactive carbon that a modern piece of charcoal has. So it must have lost. Over the years, it lost. If it only contains 15% of what modern charcoal has, it must have lost 85%. Okay. I'm not sure if that's important, but so it's been around a while. It lost. Yeah, okay. The question is, how old is it? So I'm looking for the time it takes to lose 85%.
So
Maybe that's what I'm looking for. And I don't ever really know the initial amount, but I think that's okay. I can kind of do this problem with an unknown initial amount. I got K now. I'm just going to use this for K. It's almost easier than writing the decimal. Do you agree?
Yeah.
I mean,
That's what I would do.
so there's my K. And I don't know the initial amount, but here's what I know: in a certain amount of time, I will lose 85% of the charcoal of the 80. God, I will lose 85% of the radioactive carbon. Meaning, if I lose 85%, how much do I retain? 15%. So even though I don't know what C is,
That's 0.15.
I want to know the time it takes to reach
15.
0.15 C. Beautiful.
Okay, so you're saying basically you 50% and C would be 100%, you're just dividing it, right?
Yes. Or again, the way I want to talk is that I don't know C, but in so many years I'll have 15% of C.
15% of C.
And at first that looks like, oh, well, you don't know C, you can't go any further. No, if you divide by C, it's gone, and you don't really ever need C. Right, right. And we can find the time it takes. We can find the time it takes to go to lose 85% of your stuff, or to retain 15% of your stuff. Right, we can find this time. 0.15 equals e to this natural log of a half.
So we would have to ln both sides. Right?
So we would try to get rid of this e by ln'ing both sides. The ln of 0.15 equals, the ln will cancel this e, but it will leave me with this. I'm going to write it like this. I'm going to call that a 0.5, by the way. It's a half. Is that okay with you? All right, all you guys got to do is solve for t. Divide by this big dude? Or, let's see, another couple ways to think. I might multiply the 5715 up top times the ln of 1.15. I might divide by the ln of 0.5.
I'm gonna set the k for x real quick, and then I would just say ln of 0.15 divided by x on my calculator, since I set k for that, and I get 15,641 some change.
Is that what you guys got? 15,000
641.
and point.
0.75.
Okay, hold on. Thank you. These are years. So if they're years, I don't need too many decimals. That's 15,641, 642 years. Cool. That was cool. You know, all these problems are cool, but I don't know if you've noticed, it's the same thing. We're doing the same thing every time. I mean, when we're working with this model, I mean, maybe it's not all the same thing. We're trying to find C and K. I guess right here, some of these recent problems here, you can work with these problems without ever knowing C.
Yeah.
But we're kind of doing the same old algebra over and over again. We're not even really doing calculus, in case you haven't noticed.
Oh, sorry. As it's focused mostly on in chapter 6, or is it something we'll be seeing throughout the semester?
Yeah, right. No, we don't. Yeah, right. So we're in this little topic called differential equations, where these kind of cool things arise. The rest of this course, we've got other topics that aren't really much related to this, right? In a way. Right. When you come back and actually take differential equations class, we'll see this again. I'll do it quickly. I'll run through some of these ideas again, but along with a lot of other ideas. Well, anyway, that's pretty cool. I mean, that is what they do, I guess. They dig up some more old charcoal and analyze it and do a little carbon-14 dating, you know, to determine how old it is. That's pretty cool. Okay, let's, I got another idea. So I want to do something else. Do you guys need a little break? It's
Sure.
all right. Let's. I don't like 15 or 20-minute breaks. So how about 5 to 7 minute break, and then we'll just come back and